Hello everyone. So I'm going to walk through the odd numbered exercise for chapter 7 of your textbook so we can go over how it is that we're going to use inferential statistics, the idea that we're drawing a sample from our population and comparing our sample to where it came from in the population. So let's get started with these exercises. Question 1 asks us, please calculate the population standard error of the mean. So sigma with a subscript of x bar. This is equal to the sigma that we're given for the population divided by the square root of n. N is our sample size. So let's do A. Eight divided by the square root of 16. The square root of 16 is 4. 4 times 4 is 16. So 8 divided by 4 equals 2. Okay? And it really is that simple. The trick here is to make sure that you are remembering to take the square root of the denominator. So let's do E. The population standard error is equal to the population standard deviation, which is 32.86 divided by the square root of n, which is 31. Now I'm going to get my calculator out and get the square root of 31, and that equals 5.57. 32.86 divided by 5.57 gives me 5.899, so that's actually 5.90. There we go. So hit pause and do C and D, and I'll write down the answers to those. And 0.88. Okay, so nothing difficult there. Let's move on to the next one. For each of the following situations, calculate the z statistic. Okay, let's start with A. Z is going to be the same. Z equals x bar minus mu divided by, now we're dealing with a sample, so it's going to be our population standard error. I'll calculate that first. 6 divided by the square root of 36. Well, the square root of 36 is 6, because 6 times 6 is 36. 6 divided by 6 is 1. X bar is 14.00 minus 11.00 equals 3 divided by 1 equals 3. So Z equals 3. Okay. Same steps for each one, no matter what it is. Start with my original equation. And if I wanted to, I could make this, oops, I could sort of put a fraction within a fraction. So I'll do one more. Let's do D. First things first, we'll calculate the standard error. Equals 4. 4.59 divided by the square root of 26. The square root of 26. Oops. Just turn your phone sideways. Square root of 26 is 5.099, so I'm going to call that 5.10. 4.59 divided by 5.10 equals 0.9. So now back to our z. Z equals 10.12 minus 7.98 divided by 0.9. First start with the numerator. 10.12 minus 7.98, 2.14 divided by 0.9. The answer is 2.3777, so let's call that 2.38. Okay. So hit pause and do B and C, and I'll write the answers down. So B, we actually have a negative Z, negative 1.00, and C, we get Z equals 2.43. So again, with these, you have to break it down into two steps. First step, calculate the standard error. Second step, find Z. For each of the following situations, calculate the Z statistic, make a decision about the null hypothesis, and indicate a level of significance. Okay, so for this one, what we need to do is act as if we are testing a hypothesis, and we're going to see if our sample is different from the population, and in that case we will see whether it goes past the cutoff. So let's do a z-score. Z equals x bar minus mu divided by standard error, which we're given this time. So let's do A. 40 minus 30 divided by 10 equals 10 divided by 10 equals a z-score of 1.00. Now bucket that on the floor, and we know we're starting at going out to 1. Is that past the 1.96 that we need in order to reject the null hypothesis? No, it's not. So here we would do not reject. And we would do not reject because the probability is greater than, remember, the alligator eats the bigger dinner, 0.05. Reject because probability is greater than 0.05. That's how we do that. Let's just skip to the hard one. Let's go ahead and do D. For D, again, we're given all the information to calculate Z. 132.65 minus 154.90. Might look scary, but so what? I mean, it's just a number. Just because there's decimal points shouldn't make it any harder. We're still typing into our calculators. 132.65 minus 154.90. going to get a negative number. Negative 22.25 divided by 11.79 is a negative 1.88. Actually 1.89. 1.887. So we're going to round that up. 1.89. Again, bucket on the floor. Draw our curve. We know that the decision for rejection, if we want 95%, is going to be at 1.96. Again, I've just memorized this. 95% confidence, standard normal distribution. We want 0.05 in the tails. Two-tailed test. .96 is our magic number. Now this is a negative 1.89. It's close, but not quite. So we will do not reject, because the probability of getting this number is, this sample mean is greater than 0.005. There we go. Now let's do one where we're going to reject. So I know the answers, so let's do C. Spoilers. Calculate the z-score. 19.23 minus 15.01 with a standard error of 1.47. Let's let our calculators do the math. 19.23 minus 15.01 is 4.22 divided by 1.47, and that equals 2.8707. Okay, 2.87. So what does that mean? Well, draw a curve. We know that at 1.96 is our magic number. We're actually at 2.87. I'm going to have to find me a chart and look it up, see how much is in that tail of that curve for that high of a z-score. There we go. 2.8, go over to 7.9979. That is not a lot left in these tails. So that is 0.9979. That's less than 1%. That's a really small probability that we are going to get that sample mean from the population. So we are going to definitely reject the null hypothesis that they're the same. And it's because the probability is less than, you always point on the pick on the smaller one, 0.01. Okay. All right. So if you go ahead and do 5B, the z-score is 1.71, and we're not going to reject again because it's less than 1.96. It's less than, the probability of getting that is more than 0.05%. Number 7. For each of the following situations, calculate the population standard error of the mean and the z-statistic, make a decision about the null hypothesis, and indicate the level of significance. This is just like the last one. I'm only going to do one of these. Let's pick I don't know, let's pick C. First step, I've been given X, I've been given mu, I've been given sigma, and I've been given N. So I need to turn that sigma into the standard error by calculating sigma over the square root of n, 3.28 divided by the square root of 19. Grab my calculator. The square root of 19 is 4.36. Now I'm just rounding to 2 digits. 3.28 divided by 4.36 is equal to 0.752. 0.75. My z is now going to be x minus mu divided by the standard error. Same equation, essentially. 8.11 minus 10.12 divided by what we just calculated, 0.75. Well, 8.11 minus 10.12 is a negative 2.01. Divide that by 0.75. We're going to end up with a negative 2.68. What's that mean? There's our normal curve, 0. If we're using 95% confidence, we want 1.96. We get a negative 2.68. That means, looking it up on our z table, 2.68. Wow, that there is 0.0037. So it's less than 1%. Here in the tail, we would reject the null hypothesis because the probability is less than 0.01. Now, as you do the rest of these, hit pause, go ahead and do A and B, and I'll write these, give you the answers. So for A, your standard error is 1.00. Z is going to equal 2.00. Because it's greater than 1.96, you would reject the null. For B, let's see, your standard error is 2.28. That gives you a z-score of 2.09. And again, you would reject because of the probability is less than 0.05. Okay. Oh, finally, an actual question. Number 9. Students applying to grad schools are required to take the GRE. I did. Let's say an enterprising student develops a course she believes will increase students' GRE scores. She develops a sample of 25 students. N is going to be 25. Believed to be representative of the larger college student population, and puts them through this course. Next, they take the GRE and receive a mean score. So her sample mean score is 1075. Assuming that the GRE has a population mean of 1,000, which we can actually know because as a standardized test, they actually publish their distributions, and a standard deviation, population-wise, of 200. Does the course appear to significantly increase GRE scores? State the null and alternative hypothesis. Allow for the possibility that the average GRE score may be less than 1,000. This here is a sign that we're going to have a hypothesis test that would actually allow you to have a negative z-score, and so it'll be a two-tailed test. So our null hypothesis is that the sample mean and the population mean are the same. So essentially that there is no difference between the people who took the test and the people who took the course and then took the test. Our alternative hypothesis is that they're not the same, that they're not equal. Now you could use the actual numbers given, so you could say that the null hypothesis is that the sample mean is equal to 1,000, or that the sample mean isn't equal to 1,000. Excuse me. I don't like that. I like this one better. B, make a decision about the null hypothesis. Okay. Set alpha. That's easy. Alpha is always 0.05. Identify the critical values and state a decision rule. Well, because we have the population statistics, we're going to use the z-table. The critical value for 0.05 is 1.96. If we calculate z to either be greater than 1.96 or less than negative 1.96, then we will reject the null hypothesis. 2. Calculate a z-test for one mean. Okay, first things first, we have to calculate our standard error. Standard error is 200 divided by the square root of 25, which is 5. I'm sorry, yeah. I got thrown off there for a second because I thought 200 was a really large number, and it is because we're dealing with the GREs. Divided by 5 equals 40. Okay, so that's our standard error. To calculate z, we're going to do 1075 minus 1,000 divided by 40 equals 75 divided by 40, which according to my calculator equals 1.875, which is 1.88. Now 1.88 is not greater than 1.96, so we do not reject the null hypothesis, because the probability is less than, sorry, not less than, greater than 0.005. Draw a conclusion from the analysis. Well, I can't reject the null hypothesis, so the mean score, although higher, is not significantly different from the population mean. So we can't support the student's belief that their course significantly increases GRE scores. There we go. I will note, though, what would happen, this isn't part of the question, what would happen if we had a directional hypothesis and we said that this test could only make it better? And what we want to do is we want to pack all of that 5% error here in this positive tail. So what we would do is we would look for, on our table, the value that gives us 0.95, which is a 1.65. So if we're willing to put all of that 5% in the main tail, the positive tail, to say that it increases, then you could reject the null hypothesis. But you're going to have to, again, explain why you're using a one-tailed test instead of a two-tailed test. Let's look at another study. Personal values of 116 students studying mortuary science with the intention of becoming funeral directors. The students completed a well-established survey measuring different work-related values, one of which was the extent to which the student valued social interaction. Since one of you has a dad that does this, we will leave our comments to ourselves, and I didn't pick this. The researchers tested the difference between the mean social interaction score of these students and with an estimated population mean and a standard deviation of blah. Okay, so we're given information. We've got the population mean. We've got a standard deviation. We've got a sample mean, and we've got a sample size, 116. Okay. State the null and alternative hypotheses. Well, the null hypothesis says that there is no difference between those who are interested in mortuary science and those who aren't interested in mortuary science. So our sample mean should be about the same as our population mean. Our alternative hypothesis, they're different. Make a decision about the null hypothesis. Okay, that's easy. Set alpha. Alpha is going to be 0.05. Identify the critical values, 1.96, and state a decision rule. Well, we will reject if the probability is less than 0.05. B2, calculate a statistic. Z-test for one mean. Okay. First, we need to get our standard error, which is the standard deviation, 2.87, divided by the square root of 116. That's a pretty good size sample, so we're going to have a larger denominator, which means we'll have a smaller standard error. $116 is 10.77. 2.87 divided by 10.77 equals 0.266. Well, let's just call that 27. And our z is going to equal the difference in the means, 12.91. So these are the 12.91 is the average for those who are interested in mortuary science, minus the population divided by the standard error. Sorry. $12.91 minus 14.5. That's a negative 1.59 divided by 0.27. Negative 5.88. So let's take a look at this. Draw a normal curve. We've said that we're going to reject the null hypothesis that there is no difference at either a positive 1.96 or a negative 1.96. We just got a negative 588. There's virtually nothing left in that tail. So we would reject the null hypothesis because the probability is less than 0.05. So the mean social interaction value for the 116 mortuary science students is significantly lower than the population mean. It suggests that mortuary science students don't appear to value social interaction as part of their jobs. That's that one. The next one. For each of the following situations, calculate the standard error of the mean. Standard error of the mean, you notice we got a small s. It looks like we're headed into a land where we don't have population statistics, so we're going to have to estimate given our sample. The standard error of the mean is equal to s divided by the square root of n. Pretty similar to the last one. So for A, square root of 49 is 7. 7 divided by 7 is 1. There we go. Let's go to D, the hardest one. Divided by the square root of 54. Might actually have to use my calculator here. So the square root of 54, this is 7.3484, so let's round that up, 7.35, 2561 divided by 7.35, enter, equals 3.4849. Okay. So go ahead and hit pause and just calculate B. And then when you're done, hit unpause, and I will write the letters, or write the answer. So that's 13. 15. For each of the following sets of numbers, calculate the sample size, the mean, the standard deviation, and the standard error of the mean. Okay, this is easy. This is old school. We can do this. So this is giving us a set of data, and what we have to do to calculate the sample size is really simple. We just have to see how many numbers are in our data set. So let's go ahead, and I only want to do one of these, so let's go ahead and do the hardest one. Let's do E. So the first thing is the sample size, N. N is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. N equals 15. What is the next thing? The mean. Okay. The mean is the total sum, so the sum of x divided by n. So let's add up the sum of x. Just going to use the calculator. 82 plus, and this is where your calculator skills and your ability to type is the only barrier to figuring the answer out. I usually slow down because I want to do it correctly. And not lose my place. Alright, so the sum of x is 1083 divided by 15, 72.2. The next thing I need to calculate is the standard deviation. We'll go all the way back to chapter 4 for that one. To calculate the standard deviation. All the way back. S equals the sum of the difference squared divided by n minus 1, and we're going to take the square root of that. So hopefully I've got a nice big sheet of paper, because I'm going to have to go through and do 82, 69, 51 minus 72.2. So I would do that for all of these. So 82 minus 72.2, 9.8. 69 minus 72.2 is a negative 3.2. Alright, so we go down through and we do all that step by step. So that's x minus x bar. The next thing is to square it. So 9.8 squared, or 9.8 times 9.8. That's 96.04. 3.2, negative 3.2 times a negative 3.2 is a positive 10.24. And again, we go down and we do all that. Once we do that, then we'll have the sum. And then we divide by n minus 1. N minus 1 is going to be 14. So we take that number, divide it by 14, take the square root. I don't want to do this for the next half an hour, so I'm going to cheat. And I'm just going to write down that this is 15.27. The last thing it asks us to calculate is the standard error of the mean, and that is our S, 15.27, divided by the square root of n, the square root of 15, is 3.87. 15.27 divided by 3.87 is equal to 3.94. So there we go. Nothing hard about this one. Just doing this work here, which I refuse to do. 17. For each of the following situations, calculate the t statistic. So this is a different table. Remember, we're probably going to use the middle column and the one I gave out, but t is equal to the difference between the mean divided by the sample standard error mean. Okay, so again, we're just going to plug numbers in. Calculate t, fine. Well, let's do c. 4.25 minus 4.25 divided by 0.75, 0 divided by 0.75 equals 0. So what does this mean? Well, I like this question for a reason. We draw our t-curve. Again, it looks normal. Our population mean is at 4.25. Our sample mean is also at 4.25. They're right on top of each other. There's no difference between our sample mean and our population mean. None at all. There's no difference. So the t-value is probably going to be 0.5 if I looked it up. All right. Let's do another one. So for here, t equals 0.00. Let's do b. T equals 6 minus 9 divided by 1.5. 3 divided by 1.5 is 2.00. There we go. Oops, I made a mistake. I was doing that too quickly. 6 minus 9 is negative 3, which makes it a negative 2.0. Negative 2.00. Now, I can't figure out if I'm going to reject the null hypothesis based upon just the t-score or not. 1.96 is not a magical number. That's only the z-scores. 1.96 is the magical number. For the t statistics, I have to look it up on the chart to see if I need to reject the null hypothesis or not, depending upon the number of degrees of freedom that we have. For each of the following situations, calculate the t-statistic. More of the same. But now they haven't given us the standard error. So again, we have to calculate that. Standard error is equal to 3.23 divided by the square root of our n. My calculator decided to turn off. Sorry about that. Square root of 46 is 6.78. 3.23 divided by 6.78. 0.476, so let's call that 0.48. Now to calculate t, we're going to subtract 1621 minus 15 divided by 0.48. 1.21 divided by 0.48. 2.5208. So t is equal to 2.52. Alright, hit pause, do D and E. When you're done, hit unpause, and then I'll write the answers down and you can check to make sure you got it correctly. Got to watch out for those negative signs. For 21, for each of the following calculations, calculate the t-statistic. Okay, looking at your answers, how is the t-statistic affected by the size of the difference between the sample mean and the population mean? Well, let's just think about this, okay? The size of the difference between the population mean and the sample mean. So thinking logically from our normal curve, right? As our difference gets bigger, because the units of difference are all the same, our t-score is going to get bigger. So the difference between A, which is 2, the difference between B, which is 7, and the difference between C, which is 8, our t-score is going to get bigger because we're now 2 units away, 7 units away, 8 units away. This clue here of the standard error being 1, the greater the difference between the sample mean and the population mean, the greater the absolute value of this t-statistic. And it was nice of them to keep this at 1 so that we wouldn't have to get too confused about dividing the numbers. But we're going to get bigger. We're going to go from t equals 2 to 7 to 8. Bigger the difference, the bigger the t-statistic. In situations in which these are the same. For each of the following situations, calculate the degrees of freedom. Well, that's easy. Degrees of freedom equals n minus 1. Identify the critical values of alpha being 0.05. Calculate t and make a decision about a null hypothesis. Okay. Let's do one we can reject. Let's do C. Okay. First thing, I'm given my standard error, so I don't have to calculate that. But I do have to calculate t. I've got a small sample, and I don't have population statistics. So t equals 24.76 minus 21.55 divided by 1.27. Grab your calculators, turn back on. 24.76 minus 21.55. that was the wrong button. .21 divided by 1.27 equals 2.527. So let's call that a 2.53. Yep, 2.53. All right, let's draw out a t-curve. We're at 2.53. I wonder what our cutoffs are. So this is, I need to get out my t-table. And I gave out all my t-tables in class, so I'm going to quickly look in the back of the book. Oh wait, here's a copy. Alright, so if I look at my t-table, I have degrees of freedom. So I'm going to go down to that column. The degrees of freedom equals n minus 1. So 11 degrees of freedom. And I'm going to go over to the column that has 0.025. Because I want that much in each of the tails. And when I look that up, I get a t-score of 2.201. Now the t-score that I got was greater than that. So I'm here in our area of rejection, so I'm going to reject the null. Because our probability is less than 0.05. There we go. There's our answer. Hit pause and do D, and I'll give you the answers for D. So for D, the degrees of freedom is 25. The t-score that you'll calculate is a negative 3.15. When you draw out your curve and you look for degrees of freedom of 25, 2.060 is going to allow you to reject. Well, see, they want you to do either 0.05 or 0.01, so look at both of the numbers. This is great. This is a huge t-score. So we're going to actually reject at the 0.01 level for D. .25. Again, for each of the following situations, calculate the degrees of freedom, identify the critical values, two-tailed 0.05, calculate the standard error of the mean, calculate the t, make a decision about the null. Alright, again, we're just using the same two equations here. S of x equals s divided by the square root of n. T equals x bar divided by mu divided by s of x. Degrees of freedom equals n minus 1. So you work your way through it. This is all bucket on the floor stuff. What are we trying to do? Well, once we have our degrees of freedom, we look it up in our table. We know 95% reject. Find what the critical value is. Excuse me. Find what that critical value is, and if it's greater than the critical value, you're in the tails, you reject the null hypothesis. Okay, for 27, for each of the following situations, draw a normal curve, mark the critical values, shade in the region of rejection, Compare the stated t statistic to the critical values and make a decision whether or not to reject the null hypothesis. Fine. Bucket on the floor, draw a curve. Critical value is 2.262, negative 2.262. Shade it in. Man, that's an ugly curve. If t is 1.25, we wouldn't reject. Do not. Critical value of 2.074. You've got a negative 2.5. 2.5 is bigger. Reject. This is the easiest one I've seen. T is a negative 2. Your critical value is 1.7434. Reject. And, oh, ooh, hold on a second. They're tricky. Look at what they did there. Over here they got the plus and the minus. Over here they just have the plus or the minus. Those tricky buggers. So what are they doing? For C and D, these are one-tailed tests. So they're packing it all in one of the tails. So if my critical value here is a 1.734 and I got a t of a negative 2, I do not reject. Tricky buggers. Same thing with this one. My critical value is one-tailed and I end up with a t. Let's see, if this is 1.701 and I get a negative 1.79, I can actually reject that one. Okay, pay attention. That's it. We made it. All right. So that was how to do the exercises in Chapter 7. Again, very simple. Slight change because we're dealing with a sample instead of the population number, so we have to adjust that standard error. That's it for this one. I'll see you in class. Thanks.